Welcome, my friends. In this video, I'll be discussing section 8.8, which is titled Analysis of Variance, or ANOVA. And this is also the last section in the entire book. I know, very sad. But this is a large section, so we better go ahead and get started. So we will be conducting what is called a one-way ANOVA. And ANOVA stands for Analysis of Variance. A one-way ANOVA can be used to determine if there is a difference in the mean of at least one out of 3 or more populations using the F distribution. This is the only test that we'll be doing in this class that relates to more than 2 populations. In order to do this, we will have to utilize something called the F distribution, which looks sort of similar to the chi-square distribution in that it is right-skewed. The F distribution is a right-skewed distribution, and the ANOVA test that we'll be completing is a right-tailed test, meaning we'll be finding a probability in the right tail of the distribution. Values on the F distribution are always going to be greater than or equal to 0. The exact shape of the F distribution is going to depend on actually 2 different degrees of freedom, which we'll discuss later in the video. The null and alternative hypotheses for a one-way ANOVA test will always look like this. The null hypothesis will be that all of the means that you are comparing are equal to each other. Remember, ANOVA relates to 3 or more populations, and the null hypothesis is just that all the means are equal. Now, in general, you're going to see this letter K represent the number of means or number of groups that you are comparing. So this is just written in general, so it will work for any value or any number of means. The alternative hypothesis will always be that at least one of those population means is different from the others. Note, you must write this out in words. You can't just write mu1 is not equal to mu2 is not equal to mu3, etc., because that is actually too strict. That's not what the alternative hypothesis is saying. It's saying that just at least one mean is different from the others. It's not saying they all have to be different from each other. Just at least one has to be different from the others for the alternative to be true. Okay, in this class, there's going to be 2 different ways I am going to ask you to complete an ANOVA test. And the first is with the ANOVA function in the TI-84 calculator. And I call this the easy way because it allows us to skip over one of the most involved steps of the ANOVA test, which is creating the ANOVA table. But you really do need some practice looking at and creating ANOVA tables because you're going to see them all over the place. So this is not going to be the only way I'm going to ask you to do an ANOVA test. I'm also going to have you do it by making the ANOVA table. So we'll look at examples of both of these methods. Okay, just like with all hypothesis tests, we're going to be following the Fred technique, and F of Fred stands for formulate the problem. So we're going to be describing all the populations that you have, the 3, the 4, the 5, however many populations you're comparing. Got to describe them all. Describe each of the samples. Describe the quantitative variable that you're going to be collecting from all those populations. Describe each of the population means, however many that you have. And finally, set up your null and alternative hypotheses. As for conditions, the first condition is that the data from each of those samples should be roughly symmetric or only slightly skewed. And then the data from each sample should have relatively few outliers relative to the sample size. These are similar conditions that we've seen in a lot of the different tests that we've done related to the mean. Now there is one more condition related to ANOVA, and that is that the variation in the data should be roughly equal for all of the groups. And the way that the textbook advises that we check this is to compare the interquartile ranges based on the box plots. And we want to make sure that the interquartile range, which is really just the length of the box, is not more than twice as large in one group as compared to any of the other groups. So to check this, we're going to be making comparison box plots. Next, we can go to execute the calculations, and depending on the way that I've given you the information in the problem, this is where things could change ever so slightly. So if I give you the actual data, that's what I call the easier case. You can simply just enter the data into your TI-84 calculator, and you can use the ANOVA function, and that's going to sidestep the ANOVA table, and it's going to be really not too bad. Or if I don't give you the data, I'm going to give you some select pieces of information, and from that, you're going to have to create what is called the ANOVA table, which is a little bit more involved, and we'll look at later in this video. Either way, once you're done with either of these options, depending on which type of problem I'm giving you, you're going to be making a decision to either reject or fail to reject the null hypothesis based on the p-value that you would get in either of these parts. Finally, you'll draw a conclusion using the same conclusion statement that we've used for all hypothesis tests. At the alpha % level of significance, there either is, if you reject the null hypothesis, or is not, if you fail to reject the null hypothesis, enough evidence to suggest, and then you will describe your alternative hypothesis. All right, let's go ahead and look at an example when we are given the data. So what I mean by given the data is you actually have numbers that could be plugged into your TI-84 calculator. So in this case, it says the following table shows the final exam score from a sample of 5 students each from 3 different introstat sections. Now, ideally, you would have bigger sample sizes from this, but I think I used this in a video where I did everything by hand, and I wanted to make the numbers relatively, not too many numbers to make it easier. Anyways, students from each section had the same instructor and took the same final exam. And we want to know, is there enough evidence at the 5% level of significance to suggest a difference in the mean final exam score for at least one of the sections in the population? So we have 3 different populations here. We want to compare 3 different samples. We want to see if there's a difference in the population mean exam score. So we can go ahead and do step number 1, the F in Fred, which is formulate the problem. So first we have to describe the 3 populations. The 3 populations include all students from each section. We just have a sample of students from the section, but the populations would be all the students in each of those sections. The samples include the 5 students in each of the sections, so we have 3 different samples. The variable that we're dealing with is the final exam score for the students in each of those sections. And then our population means, we have 3 of them. They are the population mean final exam score for all the students individually in each of those 3 sections. Okay, our null hypothesis for an ANOVA test is always that all of the means are equal to each other. So in this case, it's going to be mu1 is equal to mu2 is equal to mu3. The alternative hypothesis should be that at least one population mean is different from the others. But we're going to be specific to our problem. We're going to say that the population mean final exam score differs for at least one out of the 3 introstat sections. Okay, next we can go ahead and we can review the conditions. And to do this, we're going to go ahead and plug these numbers into our calculator and create a box plot. So I'm going to go ahead and go to my stat list, press enter, and I'm going to clear out my first 3 lists by pressing clear and down arrow over top of each of those. And then I'm going to go ahead and I'm going to type in those numbers in my first 3 lists. Okay, now that I have all the numbers in my list, I can create comparison box plots. And to do that, I can press second and y equals, go into stat plot 1, change the option to the box plot that shows outliers. That would be this option here. Make this bigger. Change it to this option here. And then I'm going to select list number 1 for this, so second 1 to change that to list 1. I'm going to make sure the plot is on. I'm going to go up to plot 2, press enter over that, change this one to on. It looks like I've already got the correct box plot on that. And then I'm going to make sure this is list 2. That's correct. Otherwise, I can press second and 2 to change that to list 2. And then I'll go to plot 3. And it looks like that one is off. So I'm going to turn that on. Did I have plot 2 on? Yeah, I've got plot 2 on. I'm going to go back to 3. And it looks like I've got the box plot. Looks like I've got list 3 as well. So I should be all good with that one. Then I can either press second and quit. On some calculators, I might have to get out of this screen first. Otherwise, some calculators let you maybe just click right on the zoom option. And it's zoom 9 for zoom stat. And that's going to give me pictures of the 3 box plots, which I have right here. Okay, the conditions were, first we had to have roughly symmetric distributions. Now, the data from section 1 is symmetric. The best way you can tell from the box plot is if the line is right down the middle. So for number 1, it's symmetric, but for 2, it's a little bit right skewed. And for 3, it's a little bit left skewed. So if it's on the left-hand side of the box, it's actually kind of right skewed. If it's on the right-hand side of the box, it's a little bit left skewed. You may want to also look at the histogram. It's a little easier to tell if you look at the histograms. I'm going to go ahead and go to y equals. I'm going to just quickly turn off the other 2 plots. You can do it easily just from here. And then I'm going to do second y equals. And now I can look at each histogram separately. If I change this to histogram, this is a little bit, takes a little bit of time. But if I went zoom in 9, okay, it looks like it's, doesn't look like it's perfectly symmetric, but just a little bit more in this bottom one. But it looks almost uniform besides this first one. Okay, let's look at number 2. Let's change this one to histogram as well. Let's go to zoom 9. And now I've got to change the stat plots as well. Let me go to y equals and change 1 so it's off and 2 so it's on. Zoom 9. And I can see that one is looking kind of similar. There's kind of that almost that right skewed shape again. Let's go here and let's turn plot 2 off and 3 on. Second y equals. And then you can go to plot 3 and change this one to a histogram. And let's see what we get here. And this one is almost looking, yeah, like kind of like the opposite. They're pretty darn low sample sizes, honestly, so it's really hard to get a great picture of the histogram or a box plot here to really check these conditions. You'd honestly want to have a lot bigger sample size to do this. So we're seeing a little bit of skewness here, but we're going to move forward with it anyways. But that could be a possible complaint we could have about the symmetry here. There are no outliers, though, at least. We don't have any values. We don't have any dots on here, so that's a positive. And then the other thing was we wanted to check that we had the IQR, or the length of the box, should not be twice as large as any of the other boxes, if that makes any sense. And actually, the length of each of these boxes, or the IQRs, is pretty similar for all of these. So although we had a little bit of an issue in terms of the symmetry, there aren't any outliers, and the IQRs are very close. So we're going to go ahead and move forward with the test. Okay, next we're on execute the calculations. So this is where we're going to use the ANOVA function in the calculator. So here is the calculator. So we can go to stat, here over to tests, scroll up so that you're at the bottom of the list. That's the fastest way to get there. It's the very last option for ANOVA. And I believe this is the only function that doesn't prompt you with the inputs here. So we can just press second 1 for list 1, comma, second 2 for list 2, comma again, second list 3, and you'd continue to do commas and more if you had 4, 5, 6, however many means you're comparing, you'd put that many lists in there. And then you can press enter, and it's going to give us all the information for ANOVA, which I also have right here. So hopefully these numbers are the same. Yes, looks like they are. So I have all those values here and kind of the instructions that I just took to get here as well. Okay, we can see the F test statistic is what we'd call this, as well as the p-value. So let's go ahead over here, and the p-value is really the only thing that we need to worry about if we're doing the calculation this way. So the p-value was 0.2898, rounded to 4 decimal places, and technically that's the right tail p-value in the F distribution, to the right of F equals 1.38. Not as important that we think about that or draw that out for this type of problem, but when we do the ANOVA table in a minute, we will need to think about this in terms of the distribution a little bit more. Our level of significance is 0.05, they told us, and our p-value of 0.2898 is greater than that. So as you might remember, when the p-value is high, the null will fly. So we are going to be failing to reject the null hypothesis. So we didn't have enough evidence to suggest that there was a difference here based on our data. So let's go to our conclusion. So using the template statement that we had before, we would say at the 5% level of significance, there is not enough evidence, right? Since we failed to reject the null hypothesis, we say there is not enough evidence to suggest the population mean final exam score of at least one of the sections differs from the others. So that's all there is to it. So not really too bad when we're doing the calculations using the calculator. So here is a problem for you to try. Suppose we would like to know if the average sleep hours per night differs between adults in America, Canada, the UK, and Australia. Samples were taken from each population, and the results are shown below. Use this info to conduct a one-way ANOVA test at alpha equals 0.1. So go ahead and do the 4 steps of the Fred technique. Pause the video, and then, we'll go on from there. Okay, assuming that you have given that a try and finished this, we will go on to thinking about how to complete these problems when we don't have the data to just plug into our calculator. So if you're not given the data, you might be given some other information that can be used to complete the problem based on what is called an ANOVA table. Now this looks a little bit intimidating the first time you see it, but don't get too intimidated because this table is all really just built on patterns. So once you kind of recognize the patterns, which are not hard at all to get or to understand, you can easily fill in or complete one of these tables, which is basically going to be part of our execute calculation step. So let me just kind of describe this here a little bit. So we have these 2 sources of variation. These will be described a little bit more in a future slide, but we have what is called the variation between the groups and the variation within the groups. This is where it gets the name analysis of variance. We have these 2 different sources of variation. What's called the variation between your groups, because you have like 3 or more groups going on, so you can have some variation between the groups, technically between the means of the groups, and then you can have some variation also within the groups. it's actually kind of a comparison of those two variations that helps us create this table and eventually complete the test. So there are actually 3 different degrees of freedom. It's really the top 2 that are going to be important. We call them the degrees of freedom between, DFB, the degrees of freedom within, DFW, and degrees of freedom total, which is DFT. And the way that you can find those are with these little formulas here. K is the number of groups that you're comparing. So in our example that we just had, I guess the one that you just did had 4 groups. The one that we did together had 3. And then N is your total sample size. Make sure you know that's the total sample size and not like the sample size per group. We have these sum of squares values. So this is called sum of squares between, sum of squares within, and sum of squares total. These you'll never have to calculate these because the formulas for these are pretty nasty. So instead, I will always be giving you some of these. Note that you can always find the total column by adding the the total row by adding the 2 values that are above them. So if you add these 2 degrees of freedom, you get the degrees of freedom total. If you add these 2 sum of squares, you get the sum of squares total. As far as the mean square, you would be taking each of the sum of squares values and dividing by the corresponding degrees of freedom. So it's basically just this divided by this gives you this. And then we have the mean square within, which is this divided by this. And finally, at the end of the tunnel here, at the very end of the table, we have the F value, which is just dividing these 2 values. Okay, so like I said, it kind of looked like a lot. Let me just show you an example of a finished ANOVA table. And then from there, we can calculate the p-value. So you can see here that some of those patterns kind of follow. That the top 2 values always add to the third one. So 4 plus 30 is 34. 4 plus 60 is 100. And then also these values are just dividing the 2 previous values. So 40 divided by 4 is 10, and 60 divided by 30 is 2. And then finally, the F value is 10 divided by 2 is 5. So a lot of it is just patterns. Let me go over it one more time just to make sure that it kind of gets solidified in your head. The total column is just adding the 2 previous ones together. 4 plus 30 is 34. 40 plus 60 is 100. These values are each just dividing the 2 previous values. 40 divided by 4 is 10, 60 divided by 30 is 2, and finally the very last value is dividing these 2. 10 over 2 is 5. Okay, so once we've completed the ANOVA table, we can use FCDF on the TI-84 calculator to find the p-value. So if you draw the distribution, we're going to be using the F value of 5, and we'll be using that in the FCDF function as well as the top 2 degrees of freedom to calculate this value. So let's go to the TI-84 calculator to show you how this will work. So this is under second distribution. And then if you scroll down far enough, for me it's option 0, FCDF. The lower bound will always be the starting point of the shaded region, which in this case is 5. The upper bound will always be 1,000. It'll always be a right tail test. So we're always going to use 1,000 as our upper bound. Let me get rid of that little dot there. And then the 2 degrees of freedom are just these 2, the 4 and the 30. It says degrees of freedom numerator and denominator. That's because this relates to the numerator of the f function. The numerator of the f function related to this number, which related to this number, right? So that's kind of what they mean by numerator, and denominator was related to this, which relates to the 30. Okay, so we can go ahead and paste, and then we will get our answer, which in this case looks like it's about 0.0033. Okay, so the p-value is 0.0033 based on this table, which is also the area in the right tail of the distribution. So this is kind of what it amounts to find the p-value when you are doing this when you're not given the data. So it's definitely a lot more work. You'll have to complete this table, get the f-test statistic at the end, and then finally use that to calculate the p-value. Okay, before we look at a full example doing it with that method, I want to talk a little bit more about those sum of squares values that you see right here, which also in some ways relates to the mean squares. Just want to give you some intuition about what those are doing and what's going on. So this is an image from the textbook, and the variable that they were trying to consider was the height of, I guess, different stick figures in 3 different populations. So we have population 1, which is in blue. We have population 2, which is in red, and we have population 3, which is in green. And each of those people, and every single person here could have some height, and you can see the difference in the heights between all of these different people. So if we look back at the table here, we have, actually maybe it's better to look at this table. We have the sum of squares between, the sum of squares within, and the sum of squares total. So what are those things all about? So let's talk about that. Well, the sum of squares total is kind of similar to like a variance or a standard deviation type idea. It's really just measuring the spread or the variation for all of the individuals related to the overall mean. So if you calculated the overall mean based on everyone, the mean height of everyone, and then you measured the variation amongst the people, to that mean, that's really what the sum of squares total is. There's a formula for this. We're not going to go into the formulas. We're just going to be talking about the ideas here. And that's what that is. It's basically a measurement of the variation from all those values to the grand mean or the overall mean. Then we have the sum of squares between, and that's really exactly what it sounds like. So by between, we mean between each of these three groups. In other words, each of these groups has their own mean height. And the sum of squares between is measuring how different the means are between each of these three groups. And then finally, we have the sum of squares within, which is going to measure the variation just within each group. So now don't compare between the groups, just look at one group at a time and how much variation is there in just one group at a time, right? So make sure you understand the basic ideas of what is meant by these three terms. And hopefully this example helps that to some degree. All right, let's go ahead and look at a final example here that is going to put all of this together, looking at this where we create our own ANOVA table where we're not given the data, the second way that we do the ANOVA test. So in this case, they say that a hotel chain wants to investigate if the mean satisfaction level differs among 4 of its locations. We have location 1, location 2, location 3, and location 4. They survey 30 guests randomly selected from each location. The sum of squares between is 30,000, and the sum of squares total is 300,000. So they're actually giving us a few of the values in the table right there. We are asked to test to see if there is a difference in the mean satisfaction level between the 4 locations at alpha equals 0.05. It says assume roughly symmetrical distributions with equal variances and no outliers. And this is kind of giving us step 2 here with our review conditions because we don't have the data to really make the box plots. So we're just going to do this based on this statement. All right, so let's go ahead and do all the steps here. First, we need to formulate the problem. We have to describe the populations, and the populations are the 4 populations, basically all the customers at each of those locations. We have these 4 different locations, and each population would be all of the customers at those locations, at each location. The samples are going to include the 30 guests that we've collected at each of those locations. The variable is the satisfaction level. And finally, the 4 means are the population mean satisfaction levels at each of those 4 locations. Now we need to go ahead and set up our null and alternative hypotheses. The null hypothesis for an ANOVA test is always that all 4 or however many means are equal to each other. The alternative is going to be that the population mean satisfaction level differs between at least 2 out of the 4 locations. Basically, at least one of those means is not equal to the other 3. Next, we can move on to the review conditions step, which is not really possible here because we don't have the data. So we're going to trust this final statement here that says we have roughly symmetric distributions with equal variances and no outliers. Next, we can go ahead and execute the calculations. So we are given here that there are 4 different means. So I'm going to go ahead and say that k is equal to 4. We're going to need that for the ANOVA table. And then we can also find that the value of n, which is the total sample size, remember n is the total sample size, is 30 multiplied by 4, which is 120. And then we really do have to go ahead and complete this ANOVA table. So I'm going to go ahead and I'm going to fill in the sum of squares values here. So they give us the sum of squares between is 30,000. So that's going to be this value right here. And the sum of squares total is 300,000. And we know that the first 2 rows of the table always add to the total. So that means the missing value must be 270,000, which is 300,000 minus 30,000. Next, we can find a couple of these other values using either the patterns or some of the formulas. So if you have this like on a formula sheet, you might want to look at that and have this handy. You might remember this value right here is k minus 1. So k was 4, the number of groups we have, so minus 1 is going to be 3. And then I usually like to do the bottom one because I think it's easier to remember. This one's n minus 1, so it's 120 minus 1, which is 119. And then this one is basically the value 3 plus what equals 119. It's going to be 116. Or you can use the formula, it's n minus k, or 120 minus 4, which is 116. Then we can find these values by simply dividing the previous 2. So 30,000 over 3 is 10,000. 270,000 divided by 116 is approximately 2,357.59. And finally, the f-test statistic is just dividing these two values. So 10,000 over 2,357.59 is approximately 4.30. Next, we can go ahead and find the p-value, which looks like I'm already putting the answer here. It's apparently 0.0065, but let's verify that based on the calculator here. So we can go to second distribution, and we can scroll down to that option 0 for the FCDF. The lower bound is going to be the f value. It's the 4.3 that we found in the table. That'll always be the lower bound. The final value that you get from the table is really the main part of the table, the main thing we need. And then our upper bound is always going to be 1,000 because it's always going to be a right tail test. And then we need the 2 degrees of freedom right here. So the 3 and the 116 is always the top two. If I can do this. My numlock's off. There we go. 3 and 116. And then let's see. We get 0.00647, but that'll be 65 rounded to 4 decimal places, which is also the number that I have there in the picture. Okay, from there we can go ahead and we can make our decision. Our p-value is 0.0065, which is much less than 0.05. So the p-value is low, so the null has to go. So we're going to be rejecting the null hypothesis. Finally, we can go ahead and draw our conclusion using the conclusion statement. At the 5% level of significance, there is enough evidence to suggest that the population mean satisfaction level differs between at least 2 out of the 4 locations. Now, you might remember that when we've done a lot of these other tests, like the chi-square test and the independent t-test, a lot of times there would be an additional test we could do to get more information. Sometimes a confidence interval, usually it was a confidence interval for most of them. Well, there is an additional thing we could do here to get more information about specifically which of those locations differ from each other. But we are not going to do that in this video. That would be an additional step, and this is actually not covered in this class. So it's not anything you need to worry about, but there would be a next logical test, which would be to get some more information about specifically which means differ from each other. But that's something that we are not going to be covering. I think this is enough. So here is a problem for you to try. It says, suppose we are interested in knowing if the mean starting salary differs for graduates of 5 schools: Western, Grand Valley, Michigan, Michigan State, and Wayne State. The sample size is 20 from each school. The sum of squares between groups is 30,000, and the sum of squares within groups is 171,423.7. Assume symmetric distributions with no outliers and equal variances. So go ahead and pause the video and give this a shot. And since I know it's kind of a lot of information here, I will go ahead and give you some of the information after you have tried it. So I'm going to go and do part of the problem, but please pause the video at this point and try to get as much as you can started. Okay, assuming that you paused the video and given this a shot, I'm going to go ahead and set up a few of the parts here. I'm going to set up the null and alternative hypotheses. The null hypothesis is that the 5 means are equal to each other. And the alternative is that the population mean starting salary differs between at least 2 of those schools. We are given that the k value is 5. We have 5 means. And the n value, the total sample size, is 20 for each of the groups, times 5 groups is 100. And then we'll have to go ahead and fill in the table. So they tell us the sum of squares, let's see here, the sum of squares between is 30,000, and the sum of squares within is 171,423.7, which means we can find the sum of squares total by adding those two together. It's not actually necessary. We don't really need this number for anything, but just to complete the table, we could add those two together. We can also find the degrees of freedom between, which is k minus 1, or 5 minus 1, which is 4. The degrees of freedom within, which is n minus k, or 100 minus 5, which is 95. And finally, the degrees of freedom total, which is 100 minus 1, or n minus 1, which is 99. And also, we should check that 4 plus 95 does indeed equal 99. So I'll let you go ahead and complete the rest of this table using the formulas and the pattern that maybe you have learned from the table. But other than that, that is all I had to talk about in this video, and also the end of the last video of the entire class. So hopefully you have enjoyed these videos and they have been helpful for you. If so, please leave me some feedback. Let me know if there's anything that you'd like to have changed or done any different. But I spent a lot of time on these, so hopefully they have been helpful for you and have helped you get you through this class. So anyways, that's all I have to talk about in this video. So I will see you sometime, hopefully, in the future.